As a museum owner, you run a computer vision program to track visitors and analyze their circulation behavior inside the building. At each minute, it types the timestamp, the visitor ID, and the current room, so you end up with this dataset. The next step for you is to find visitors' patterns, to be able to simulate new visitors and run what-if scenarios. The mistake here would be to already start thinking about training a complex deep learning sequence model that would generate the sequence of rooms to visit and time elapsed in each. But no, we have much simpler computational techniques that suit this problem. And in general, use deep learning only when you need to use deep learning. And you should focus on solving the problem instead of necessarily using specific tools. Anyway, here we will use Markov chains. Say we want to model the journey of individuals in the professional world. We want to predict their position for the next year given their current position. We assume that someone can be in his last year in university, intern, junior, senior, or unemployed. In total, we have 5 states. Usually there is no guarantee in how positions evolve, so we will have probabilities. From analyzing data, we found out that if someone is a student, the next year's probability of being intern is 80%, junior is 10%, and unemployed is 10%. If someone is an intern, the probability of staying an intern the next year is 30%, the probability of becoming a junior is 50%, and to become unemployed is 20%. And so on for remaining cases. Basically, we will have a transition probability for each 2 possible states. And this is a Markov chain that we can use to simulate n individuals with their initial state and see where they end up after x years. This is a graph representation, but we can just have a transition matrix that contains all the probabilities. Note that a Markov chain calculates the next state starting from the current state only, regardless of the previous ones. Also, it assumes that transition probabilities don't change over time, which is not always the case in the real world. Back to our museum. What are the states of our Markov chain? The states are simply the different rooms of the museum plus a state for the entrance and the exit. And the transitions represent the probabilities of going from a room A to a room B in the next minute. And we use the Markov chain to calculate the visitor's room in the next minute given the current one. But how to calculate transition probabilities? Some probabilities are known to be equal to 0 because there is no physical way to move between the 2 rooms, like between room 1 and room 8. For remaining ones, we can do that starting from our dataset. We transform each 2 successive rows into one transition row with the room we go from and the room we go to. Then for each room, we calculate the number of times we move to each room. We'll get a map like this. Finally, we just normalize by dividing by the total number of transitions from each room. And we get our probabilities. Now, if we want to simulate a visitor, we set start state to 0, then keep moving to next states by following the probabilities, until reaching state 10, which is the exit. We can even simulate multiple visitors at once, by repeating the same process. And by simulating visits, we can do a lot of useful things, such as visualizing evolution of room presence proportions over time, efficiently schedule staff, or estimating the average duration before a visitor reaches a specific room, such as the gift shop. However, even if a Markov chain is a good start, it might not be the most accurate way to model our problem. Remember Markov chain's characteristics we talked about earlier. We said that transition to a state depends only on the current state, not previous ones. So the probability of going from a room to room 8, for example, is always the same, regardless of if we visited room 8 before or not. which is not how things work in a visit. People usually have a smaller chance to go to a room they visited before. Also, we mentioned that probabilities stay the same forever, which might not be the case for the exit room. We can say that people have a higher chance to leave over time. If a visitor reaches the exit door after a few minutes only, the probability to leave might be 5%, for example. But after say an hour, it surely increases, unlike our model that keeps the same probability regardless of time spent inside the museum. This is why we need to think about a bit different approach than the typical Markov chain. Tell me your approaches in comments. Meanwhile, we will stop here for today's episode, in which we discussed Markov chains and how to use them to simulate museum visits. You can find code in description, and see you in the next one.